For me, ladies and gentlemen, compression and issues of buckling are the most interesting part of the course. So I am sad that we are leaving this to the end of the day. I hope you can maintain your enthusiasm, because I believe that when we have a good understanding of compression, then that means we have a good understanding of lateral torsional buckling. Because a beam, if the compression flange is free to move, the compression flange thinks that it is a strut, and it behaves like a strut. So at a very simple level, you can assess lateral torsional buckling by thinking about the compression flange as a strut. When you come across the two different forms of buckling in the Eurocode, you will see that they are presented in a very similar way. So it's important this afternoon that we gain a good understanding of how the Eurocode deals with compression. There are in fact 4 modes of buckling covered by the Eurocode, and here they are. So flexural buckling, that would be the common form of buckling under compression. So if you're designing a column, for example, or a bracing member subject to pure compression, the Eurocode describes that as flexural buckling. If a beam is unrestrained, then the Eurocode describes that as lateral torsional buckling. But there are another 2 forms of buckling under pure compression. They are torsional buckling and torsional flexural buckling. This is torsional buckling. You will find that torsional buckling is only critical if you have a cruciform section. So these sections are symmetric in both axes. This cross-section is drawn midway up the column. The column is being subject to pure compression. So all of this cross-section feels compression. Anything in compression wishes to buckle in the minor axis direction. So as far as this area is concerned, it wishes to buckle in the minor axis, which, for example, may be in this direction. And all of these flanges wish to buckle in the same direction. So instead of a lateral movement, it's a twist. So if I have one end of the member and you have the other end of the member, it twists to the midpoint and then twists back the other way. That would be torsional buckling. It's a phenomenon which occurs with I sections as well, but for I sections you will find that it is not critical. It will always be minor axis buckling for I sections of a given length rather than torsional buckling. You would get the same effect if it were a cruciform section with flanges. The flanges are subject to compression, they wish to buckle. Eventually they will buckle in the minor axis direction and you get this twisting behaviour. This is torsional flexural buckling. So this would happen with an asymmetric section. Some sections like this are rolled in the UK with a different flange top and bottom. Let's imagine that for some strange reason we wish to design a strut using an asymmetric section. So at the mid-height of this member, the whole of the cross-section experiences compression. You know that it wishes to buckle generally in the minor axis. What stops it buckling in the minor axis is the resistance of the flanges, generally in bending. Here we have a large flange with large resistance. Here we have a small flange, modest resistance, and therefore will move further. So not only do we get a lateral movement, we also get a torsional movement as well. So that's torsional flexural buckling. These 2 forms of buckling are unusual. They are unusual because not many people decide to use a cruciform section as a strut. not many people decide to use an asymmetric section as a strut. So the very common case that we come across almost always is just ordinary flexural buckling. Perhaps you turn, as well as looking at my PowerPoint, perhaps you would turn to page 48 of this guide. So at the top of page 48, we want the resistance to be greater than the design effects. The design resistance must be greater than the design effects. And then the design the design resistance is giving you the next formula down. N is for axial compression, B is for buckling, RD is for design resistance, and that's a reduction factor chi multiplied by the area multiplied by the yield strength divided, notice, by gamma M1, because we've left cross-sectional resistance behind. Now we are dealing with buckling, and buckling involves gamma M1. Notice that that formula is for class 1, 2 and 3 sections, because the area in that formula is the gross area. If you were in a class 4 section, you would replace the area there with the effective area. So we need to calculate this reduction factor chi. So under section 6.3.1.2, you will see a formula for chi. It involves a couple of things. It involves the variable phi and lambda bar. And this confuses us in the UK because sometimes we think that lambda bar is lambda to the power of -2, because we have never met this expression before. But actually, it's lambda bar squared in that particular formula. So we need to calculate phi, and we need to calculate lambda bar. And on the next line, you see a formula for phi, 0.5 into a bracket, 1 plus alpha, so on. Lambda bar reappears in that formula. So now we need to calculate lambda bar, and we need to know alpha. Alpha is going to come from the table at the bottom of the page, table 6.1. So you'll see various values for alpha, and that depends on the curve. A0, A, B, C, or D. And the choice of curve comes from page 49. So normally we would start off on page 49, and we would say, have we got a rolled section or have we got a welded section? Is it tall and narrow, or is it short and wide? Which axis are we interested in, the major axis or the minor axis? What grade of steel are we using? And that will identify the curve for us. So we would choose the curve from page 49, and then we would look at the bottom of page 48 for the imperfection factor. Then we need to calculate lambda bar. So the general formula is given you on page 48. Lambda bar is the root of the area times the yield strength divided by n crit. And maybe in the Ukraine you are very familiar with n crit. In the UK, we had no idea what n crit was. It says in the Eurocode that it is the elastic critical buckling load, and designers are expected to know what NCRIT is. In the UK, we would have to turn to some other authoritative guidance, because NCRIT is not really part of our undergraduate education. I do remember NCRIT, but I would know it as the Euler load. He was a Swiss mathematician. So NCRIT and the Euler load, they are one and the same. And I know some people in the audience know about NCRIT because you were pointing out pi squared EI over L squared. So for ordinary flexural buckling, NCRIT is very easy, very straightforward. For torsional buckling, it starts to get a little bit more complicated. But within this formula, these are all either section properties or they are constants. So this is the shear modulus. This is Young's modulus, or the modulus of elasticity. This is a section property, the warping inertia. This is a section property, the torsional inertia. So actually, this is really to do with section properties, and if you are calculating the elastic critical buckling load for torsional buckling, you should really put it in a spreadsheet. That would make your job easy. For torsional flexural buckling, this is very difficult. And I think should be left to professors. So, for flexural buckling is very easy. For the other forms of buckling, particularly torsional flexural, is quite difficult. But for flexural buckling, if you look at page 48, there is an alternative way to calculate lambda bar. But please note, it's only for flexural buckling. You should not consider that to be a limitation, because flexural buckling is the most common form of buckling that we do, that we consider in our day-to-day design process. So the alternative expression then is the length, and that would be the buckling length, by the way. So you as designers must decide what the buckling length is. You might have the concept of an effective length, which might be less than the system length, or might actually be more than the system length. The Eurocode invites you as a designer to decide what the buckling length is. Divided by, lowercase I, is the radius of gyration. So that would be a section property that you would either calculate or you would find in some tables. And then divided by lambda 1, and lambda 1 is a constant. And towards the bottom of page 48 of this guide, you will see that it's 93.9 multiplied by epsilon. And because in the Ukraine you tend to use S235 steel, epsilon will be 1. So your value of constant will be 93.9. In the UK, we tend to use S355 steel, so I am familiar with lambda 1 being 76. The two expressions, either the general expression with the Euler load on the left-hand side, is precisely the same as length divided by radius of gyration divided by this constant. If you start at the left-hand side and use algebra and rearrange the formula, you will be able to demonstrate they are one and the same. So then we have a number of curves. A naught, A, B, C, or D. And if we feel mathematical, we would then use the expressions halfway up page 48. But why would anybody want to do that? Because on page 50, you have a graph. So along the bottom you have slenderness, lambda bar, and up the left hand side you have the reduction factor chi. So once you've calculated the slenderness and have identified the curve, be careful about the choice of the curve, because remember there is an A naught curve as well here. Once you've identified the curve, then you can simply interrogate the graph, read across to the left, and that will tell you chi. Personally, although we have the graph in our guides as well, I think this is a little bit imprecise. So another option for you is on page 51, and you have a lookup table. So at the top we have the different curves, A naught, A, B, C or D, and down the left hand side we have the slenderness lambda bar. So in actual fact, this afternoon you have a number of options, because when you calculate the slenderness lambda bar, you can either use the root of area times yield divided by n crit, that's the general expression, or halfway down page 48 you can use L over I, the radius of gyration, divided by lambda 1, the constant, which would be 93. You certainly need to select the buckling curve from page 49, and then you can calculate the reduction factor. You could either use the maths on page 48, you could use the figure on page 50, or you could use the lookup table on page 51. Personally, I recommend using the lookup table. So I'm going to give you a demonstration now. This is for a rolled section, and then I'm going to ask you to have a go at the member which you previously classified. So here is a universal column section. So this is 203 by 203, so approximately square, 60 kilograms per metre, and it's 6 metres long. So armed with your guide, you will start off on page 49. And you will be in the top row of page 49 because this is a rolled section. And then we need to decide the H over B ratio, so 203 divided by 203 is about 1. We are less than 1.2. First of all, how thick is the flange? Well, I can tell you it's less than 100 millimetres thick. And we're interested for the moment in the minor axis. So we are on curve C. It's very straightforward. So then I need to calculate the non-dimensional slenderness lambda bar. And I have two ways to do it. And here they both are. I'm going to start, because this would be the familiar way in the UK, to do the length divided by the radius of gyration divided by this constant lambda 1. Now it's convenient for me because I'm using a rolled section, so I would simply look in my very valuable blue book, the most expensive book that the SCI produces, the most boring book that the SCI produces, but it has the radius of gyration for a universal column. You probably can't read it, but it's 5.2 centimetres. Okay, so length divided by radius of gyration divided by lambda 1. I'm using S355 steel, so epsilon is less than 1, and lambda 1 is 76. So length divided by radius of gyration divided by this constant gives me a non-dimensional slenderness of 1.51. So if I wished, I could then use the figure that you have in your guide. I know where I am on the bottom axis, 1.51. I know which curve that I need to interrogate. And over on the left-hand side, I think that would give me a value of the reduction factor chi of 0.31. Alternatively, and we'll see this later, I could calculate. But for the moment, let's assume that chi is 0.31. Then the resistance is chi times area times yield, because we're buckling, divided by gamma m1. Now, we know what the area is from lookup tables. We just need to pause about the design strength that we're going to use. Because remember, the design strength varies with the thickness, and for today, the design strength varies with the thickness of the flange. As I said earlier, the thickness of the flange governs the design strength of the whole cross-section. So from my lookup tables, the flange is less than 16 millimeters. The first reduction in strength comes at 16 millimeters. So I'm going to use the full design strength of 355. I use my section property tables to tell me the area. So chi, the reduction factor, multiplied by area, multiplied by yield, divided by gamma m1, gives me 841 kilonewtons. Let's try it the other way around. Let's try the general approach. I need to work out n crit. So this is the second moment of area, or the moment of inertia, perhaps you call it, in the minor axis. So from some lookup tables, I've extracted that particular value. I calculate n crit, and the reason why I don't like this approach is I have no sense as to whether this is an appropriate number. I don't have enough experience to say this is correct or this looks silly. Maybe you do, but for me, that number is not very transparent. There is the general expression, the root of area times yield. Remember, that value of yield might change with thickness, divided by n crit, and of course, it gives the same answer. So I could use the graph, if I wished. Or I could calculate, because on page 48 of your guide, I know that curve C means the imperfection factor is 0.49. So if I was feeling mathematical, then I could simply substitute 0.49 for alpha and 1.51 for the slenderness. I calculate phi, and then I substitute the things that I know in the formula for chi, and I calculate 1.51. No, I calculate 0.31. Same calculation here then. Reduction factor chi, area from section property tables, yield, which depends on the thickness of the flange. We're in buckling, so it's gamma m1, which is 1.0. Same answer. Let's have a look then at torsional buckling. So first of all, lowercase I is the radius of gyration. So from section property tables, I'm going to identify the radius of gyration in the minor axis, We saw this value before, except it was expressed in centimetres. It's 5.2 centimetres. And this is the major axis radius of gyration. Everything else is a constant, Young's modulus, modulus of elasticity, you might know it as. I know this is the shear modulus. These values are going to be provided by section property tables, the warping inertia and the torsional inertia. I then calculate the elastic critical buckling load. And again, I have no feel for that. I don't know whether that's wrong by 100, 1,000, a million, whatever. Oh, there is somebody coming to the front for me. Because now I am considering torsional buckling, I have to use the general expression, because that special rule was only for flexural buckling. So I must use the general expression, the root of area times yield divided by n crit. So here we go, and the value for lambda bar is 0.766. And then the Eurocode says for torsional buckling, which curve do we use? And the curve we use is the curve that we use for minor axis flexural buckling. That's what the Eurocode says. We already know that the curve for minor axis flexural buckling is curve C. We identified that earlier on. So we could use the figure, we could do it mathematically, or we could use the lookup tables. I've chosen to do it mathematically. So I'm simply substituting alpha again. So curve C, you'll recall, the imperfection factor was 0.49. Here is me substituting lambda bar. The answer for 5 is 0.93. Substituting the calculation for the reduction factor chi, the answer is 0.683. And the resistance, I'm sure we will be familiar with this now, is the reduction factor chi times area times yield, which depends on flange thickness. And because we are in buckling, we divide by gamma m1. So the two answers are 841 and 1854. In the UK, I would joke now and say, who would ever want to do that by hand? Because for rolled sections, the most expensive but the most boring book in the whole world has lookup tables. So our design practice in the UK would be to say, here is the member, 203, 203.60. Here is a buckling length of 6 meters. And according to the lookup tables, the minor axis flexural resistance is 844. And the torsional resistance here is 1850. And you might say, well, your numbers weren't precisely the same. And that's because I rounded at some part of the calculation process. Maybe I didn't use enough decimal places. If I'd have used plenty of decimal places, I would have got these values. It's going to be more difficult for you, ladies and gentlemen, because my understanding is that you do not have lookup tables. So you'll need to calculate these things each time. So, conclusion from me with this, what I think is a very important session. Please remember that flexural buckling, that's what the Eurocode describes it, is the sort of buckling under compression that you will find, I believe, 99% of the time. Because you are generally not using cruciform sections, you are not using asymmetric sections. There are then two ways to calculate lambda bar. They're in your guide on page 48. You can either use the general expression, you need the Euler buckling load, or length divided by radius of gyration divided by that constant lambda 1. Once you've got the slenderness and once you've identified the curve, then you have three ways then to calculate the reduction factor. You can use the figure, a little bit imprecise, I believe. You can be mathematical, why not? If you want an easy life, you would use the lookup tables.